Here is an introduction to solar system life to accompany chapter 30 of the textbook Astronomy from Open Stax. Obviously, the only place that we know of in the universe and in the solar system with confirmed life is Earth, but mostly what I want to focus on here are the several, potentially habitable environments or formerly habitable environments in the solar system, because surprisingly there are a lot of them. So there's, evidence of past liquid water on some objects. There's evidence of subterranean oceans for several moons. And if you get creative, then you could even have methane-based life on, for instance, on Titan. Go into each of these in more detail, but just for instance, if you look at the habitability zone for the sun as a function of time, it obviously changes because luminosity changes with time, as we covered in the past when we talked about stellar nuclear burning. And you can see, planets will pass in and out of being, favorably habitable over time. And as we've talked about in the past, your habitable zone can extend far beyond what you'd expect just from the temperature based on the star, because moons, tidal heating on moons can cause habitable conditions. So let's just start at the inner part of the solar system and work our way out. So with Venus, you might consider, okay, this could be a habitable environment just to first order because the solar flux was not as high. It's steadily increasing over time as hydrogen is converted to helium in the core. And we believe that the early atmosphere of Venus probably had a lot more water and fewer greenhouse gases. So there wasn't a runaway greenhouse effect yet that essentially evaporated away all of the water. And so climate models of Venus suggest that it was habitable for the first couple billion years of the solar system. So for instance, the average surface temperature on Venus was pretty reasonable, right? In the handful or tens of degrees Celsius. So definitely, at least conducive to hosting liquid water and to hosting life. In principle, present-day Venus could be hospitable to life in the atmosphere, so the surface is extremely hot, extremely high pressure, very unlikely to host any kind of life as far as what we're familiar with. But if you go into the clouds, then the temperature's not too hot and the pressures are pretty reasonable. So there's been some speculation, you could maybe have microbes floating in the clouds of Venus. And not too long ago, there was a claim of an observation of this molecule called phosphine in the atmosphere of Venus. What makes phosphine special is it's a product of decaying organic matter, and there is a claim that you can only make it from organic material. I'm not sure I believe that, to be honest. I don't know how well we know chemistry at such high pressures and densities as you have on Venus. I would highly doubt that we do know it that well. And on top of that, this is the spectral feature for phosphine that we're talking about here. So this other stuff next to it's noise. So that's for context. If that's noise and that's a feature, okay, it's not that strong of a signature. And other molecules could potentially cause this. So the jury's still out, at least as of this recording. Maybe there's some signature there, maybe not. My money would be on not. Earth, I don't need to talk about the life on Earth too much. You know that it's there, but just let me briefly comment on how life began. So, we don't know when exactly life began on Earth, but there are what we believe are fossils of microorganisms that go back to pretty shortly after the solar system formed. So, Earth is thought to be not a lot older than the solar system, about 4.5 billion years old. And these microorganisms date back to about 4 billion years old. So not a lot of time was wasted seemingly in Earth, in life starting on Earth. We of course have no idea how life began. Talked about that in the Introduction to Habitability lecture a bit. But an interesting possibility is that regardless of how it began, it didn't necessarily have to begin on Earth to be transplanted to Earth, right? So in principle, another planet in the solar system or another body could have been more conducive to life. An asteroid could have hit that surface, busted off a piece of that planet, and brought a meteoroid to Earth, and had that initial life-bearing stuff transplanted to Earth, or somehow life could have began on a comet and been brought to the Earth. So we don't really know, but those are definitely possibilities. And of course, Earth could have, or life could have begun on Earth just in some soup of molecules that more or less randomly combined and eventually became something that's like a living cell. The conditions that on the early Earth were very extreme. The surface was really hot, and so that's one reason to study so-called extremophiles, right? These are creatures on the surface of on the Earth that exist in a very extreme environment. So really high pH, really high salinity, very high temperatures. And so studying extremophiles can give us some clues as to how life maybe could have begun in the early history of the Earth. In any case, it happened, very early on in the formation of the solar system. Moving out to Mars, if you look at the geology and the chemistry on the surface of Mars, it indicates it once was covered in really big oceans of flowing water. So that's shown here in this picture, this thing called Oceanus Borealis. We believe that, based on geologic and chemical signatures, we can make out the shoreline of this vast ocean. And so it seems that there was a large oceans of flowing water on Mars. Now we just have some ice caps. And the reason this could have existed early on is that there was a lot of volcanic activity, and this enhanced greenhouse gases in the atmosphere of Mars, allowing this liquid ocean to exist for some time. Eventually, this water would be trapped in the ground, so would the carbon from the carbon dioxide, and the atmosphere would be steadily lost to space. It's a less massive object than Earth, so it would have more trouble holding on to its atmosphere. Another problem, with modern day life on Mars would be that there's not much of a magnetic field, and so you need a magnetic field to shield from solar radiation if you're that close to the sun. But there is evidence that Mars did have a relatively significant magnetic field in the past. So orbiters can measure the magnetization of the crust of the planet, and there does appear to be evidence of a past significant magnetic field. That in science fiction, you'll read about terraforming Mars, making it habitable again. That's appealing because it's going to move into the habitable zone as the sun evolves. There are a lot of complications you'd have to deal with to do that. So the temperature is very cold. There's no magnetic field. There's basically no atmosphere. It's very low pressure, and the composition isn't at all right. So there would be a lot of work to be done. And if you want to waste some time on the internet and have some fun, you can read about terraforming Mars, and there are a lot of serious but somewhat science fiction proposals on how to do this. Believe it or not, when you think about habitability, you have to take into account objects in the asteroid belt. So Ceres, is a dwarf planet present in the asteroid belt, and Vesta doesn't have hydrostatic equilibrium, but it is a very large rock. And there's water ice seemingly present on these objects. And it varies over the course of the orbit. So here you can see the amount of ice basically that you have on Ceres as a function of time, and you can see where these observations are made as a function of its orbit. But interestingly, there's water ice there. It's thought to be liquid below the surface. So Ceres still has some internal heating, from radioactivity. And so that would make it warm enough that you could have liquid water below the surface. So you could imagine maybe some microbes living in that, perhaps, it's at least possible. And if you look at Vesta, here on the surface, just from imaging it, you can look at some geologic activity or geologic signatures that look a lot like flowing water. here you're looking at a crater, and if you zoom in on the edge of this crater, you see these features here. And these look quite a bit like and are quite consistent with water flowing inside of craters on Earth. So this is meteor crater here. And so that it seems to indicate that there was some flowing liquid on the surface of Vesta at one point in time. Now the next place, when you go back further out in the solar system, you have to move away from the planets themselves because they're gas giants and ice giants, and instead focus on the moons. So the Galilean moons are particularly interesting. If we take a look at Io, at first glance it seems pretty inhospitable. So it's in the radiation belt of Jupiter, and that just means that the magnetic field concentrates energetic particles in that location. So it's going to be bombarded with radiation. It has a very thin atmosphere. It doesn't have a lot of water, so that sounds pretty inhospitable, and of course that is. But in its favor, it's a rocky object, so it's not an ice moon like the other. It's a rocky object. There's a lot of tidal heating because of where it's located, with respect to Jupiter and the other Galilean moons, and that's what causes quite a bit of volcanic activity. So it's the most volcanically active object in the solar system. And if you think about, okay, you have a rocky object, a lot of volcanic activity, that maybe then gives you some conditions conducive to life, because on Earth, hydrothermal vents are biological hotspots. So, the idea is maybe you have some subterranean life. It would have to be subterranean because you don't really have much of an atmosphere and you have a lot of radiation on the surface. But, maybe there's, a subterranean ocean here and you could have some life existing in that location, maybe. When you go to Europa, the arguments are similar, but here you have less radiation on the surface, and the geologic activity is very similar to Earth. So this fun GIF here is a overly complicated way. You can look at the basically the temperature versus the ratio of the surface area to volume. So this is kind of giving you planets that are similar are going to fall along this diagonal line here. And you see the objects with really similar geologic activity in the solar system. To Earth, you have Europa, so this Galilean moon, and then Enceladus, a moon of Saturn that we'll talk about in a moment. And so, an argument would be if you have this similar geologic activity, then perhaps you're going to be similarly conducive to life, right? Now, that's a pretty shaky argument. If you go into more detail, the most interesting thing about Europa is that you have a rocky mantle and then a liquid water ocean on top of that. So this, because you have a lot of geologic activity similar to Earth, rocky mantle, liquid ocean, this makes the presence of hydrothermal vents seem quite likely. And again, hydrothermal vents are a hotspot for life on Earth, and so why would they not be on a moon? It's definitely plausible. So when we move to another Galilean moon, let's talk about Ganymede, also thought to have subterranean oceans. The problem is that the seafloor here is thought to be covered in ice. And so you don't necessarily have this rock-ocean interface that you need to create a hydrothermal vent. Now, theorists are creative, and if you say, okay, well, that may be the case, but what if you model this thing and you introduce a lot of salt in the ocean? So this is magnesium sulfate, and when you introduce that into the ocean, you change the freezing point of water. So this phase space diagram is pressure versus the temperature. The Roman numerals 1 through 5, these are different phases of ice. And then liquid is this color over here, and what's these lines are indicating is that as you increase the salinity, then you move this freezing temperature down, basically. So you can have liquid water at cooler temperatures than you otherwise would think. And so it's plausible anyways that you maybe do have a rock-ocean interface, and therefore maybe you have hydrothermal vents, and therefore maybe you have some kind of life that could exist on Ganymede. When we look at the Galilean moon Callisto, at first glance, very inhospitable place. The surface is extremely cratered here, right? Very pockmarked. And if you have a whole lot of cratering, as we talked about in Introduction to Solar System Dating, that means the surface is extremely old, right? So there hasn't been a lot of geologic activity on this object for a long time. And you're probably picking up that geologic activity is one indicator for habitability, right? Because it can create the warm conditions that you need to have life. So the heating of Callisto also, it only comes from radioactive decay. It's not close enough to Jupiter for tidal heating to be significant. And so there's not a whole lot of internal heating. And so therefore, it's not as likely you'd have any kind of subterranean ocean or a significant one like on Europa, for instance. Now, one thing that is interesting to mention about Callisto is that though the habitability is quite low, I would say, the radiation levels are very low. It's far enough from Jupiter that it's far from the radiation belt. You're also very far from the sun at this distance. And so if you look at the radiation dose as a function of depth underneath the surface, you can see that Callisto is this dash triple dot line here. It has very low radiation levels. For comparison, Ganymede it depends on whether you're at the pole or the equator, and Europa is up here, very high surface radiation levels. So when you go to the surface of Callisto, you have quite low radiation levels, and why that's important is if you were to imagine in the far future people exploring the solar system, so going beyond the moon, going even beyond Mars, you would maybe want a big solid base to stop off at. And Callisto is pretty promising. If you want to send people out to explore around Jupiter, then Callisto could provide a resting place if you were to build a big enough base there that is habitable. It's at least an interesting idea. Moving on to Saturn, Titan is a really fun and interesting case. Not so much for liquid water-based life. It doesn't seem like that's necessarily plausible. But instead we can consider methane-based life. So one thing that you need for life, why water is so important is that it's a solvent. And instead of a solvent for organic material, instead of having water as a solvent, you could imagine methane-based life. From a purely theoretical chemistry perspective, it is completely plausible. And so what the methane-based life would breathe, rather than cellular respiration being glucose reacting with oxygen to make carbon dioxide and water, instead you'd have acetylene and hydrogen reacting to make methane. And from a just basic chemistry perspective, this is perfectly plausible. Titan also has a relatively thick atmosphere. It's the only comparable atmosphere to Earth in the solar system, and it also has the only liquid oceans in the solar system outside of Earth. Now, again, the liquid here is methane, but nonetheless, that means that Titan has weather, right? So just like you have clouds on Earth and those clouds rain water, on Titan you have clouds and those clouds rain methane. And so in principle, right, it is a very Earth-like place if you just are a little bit creative and you say rather than this sugar and oxygen-based life, or this water-based life, right, where sugar and oxygen react, instead you have methane-based life. And so when you consider the fact that you have a rocky, sort of stable substrate to live on, for life to live on, it's quite warm, so you have enough energy basically for to power chemical reactions that are needed for life. You in principle could have this methane-based chemistry, and you have this liquid solvent. That gives Titan a relatively high planetary habitability. If you use these four conditions here as your criterion, then in terms of planetary habitability, Titan beats out everything else in the solar system that you'd consider, and even several exoplanets. Another interesting object for life in terms of Saturnian moons is Enceladus. And here, the reason it's interesting is that we know that there's subterranean water because you can see plumes of water shooting out of Enceladus. Now, this GIF here only lasts a few seconds, but my understanding is it's a video of a few hours. And these sort of ray-looking things here that you see changing in feature over time, these are plumes shooting through cracks in the surface, and these contain a lot of water. And so there is some hydrothermal activity, and as we've already covered, hydrothermal activity is exciting in terms of prospective life. And then the last stop in the solar system in terms of potential habitable conditions or life-conducive conditions is Triton. So this is the very large moon of Neptune. And similar to the Galilean moons, you have a lot of tidal heating, and this may enable a subterranean water ocean. And again, we're excited about subterranean water oceans because you could have hydrothermal vents, and then you therefore could potentially have life in that ocean. Though this one's a little more tentative, it's very far out in the solar system. We know a lot less about Triton than we do, for instance, the Saturnian or the Galilean moons. And that is it for this introduction to solar system life for Astronomy 1000.